Hello and welcome to the second in a series of webcasts about data analytics. This time we're going to talk a bit about sampling, which is a pretty basic topic that everyone is familiar with that does data analysis on time signals. But there are actually some subtleties, especially when it comes to looking at things like transients and then the frequency analysis of transients. So that's the area I want to cover today. Before we get into that, I'll give a quick overview of Nyquist theorem as it's normally presented, just to get everyone up to speed, but I promise it won't be like going back to uni. It'll be a bit more rapid than that. So, how this is normally presented is we're talking about digitizing analog signals. So, in this figure, you can see there's an underlying sine wave, and then on top of that, we've got a sampled signal. So in this case, we're sampling at 1,000 hertz, so 1,000 points per second, and the underlying signal there is an 80 hertz sine wave. And you can see that the dots, which are the digitized data, represent that sine wave fairly well. So that's all good. Now, as we increase the frequency, in this case, we've now increased it to 250 hertz. What we find is that there are less dots per wavelength of the signal, or per cycle of the signal. And so now our representation, rather than being a smooth sine wave, actually looks more like a triangle wave. And then as we increase the frequency still further, we're now at, say, 498 hertz. We've only got just a little bit more than 2 samples per cycle. And what you see here is some strange things start to happen in the digital representation of the signal. So now instead of the shape we're measuring being a sine wave, it's actually, like I say, this sort of triangle wave, but it's modulated, and the amplitude at any one time doesn't really represent the amplitude of the underlying sine wave. And then, this is the whole Nyquist theorem bit, as we crank the frequency even further past 500 hertz, which is half the sample rate, we get this result, where now this is a 900 hertz sine wave being sampled at a kilohertz, and you can see that it aliases and represents itself as a 100 hertz sine wave. And so now the data you're collecting doesn't look anything like the actual underlying signal you're trying to get. So that's a sort of whistle-stop tour through aliasing, and obviously the point being that you can get valid data up to half the sample rate, and then after that you don't get a valid representation. Now, I want to now have a look at transients and how, when you sample transients, how you get different things. But actually, before I do that, I have another figure to show. When you take a Fourier transform of those signals, you see that you can represent frequencies all the way up from 0 to half the sample rate, 500 hertz. And each of these signals, because of the way we've structured the discrete Fourier transform, they're represented by single peaks in that spectrum. And there's no bleed or overlap or anything, because we've structured it to make sure that a frequency bin lands exactly on the frequency of each sine wave. And what you can see here, obviously, is all these spikes, they all have the same amplitude, even though when you look in the time domain, as we saw on some of these plots, you're getting a pretty rubbish representation of what the amplitude actually looks like. So even though you're not getting the full amplitude on every cycle in the time domain, when you do that Fourier transform, you get the correct amplitude for the sine wave, because the Fourier transform is fitting sine waves to your signal. You know, you're just saying what sine waves make up my signal. So if it's given a bunch of dots, it will try and fit a sine wave to them. And the only sine wave that fits will be that one at 498 hertz, even though those dots don't look anything like a sine wave. Right, now, moving on to talking about transients. Transients are interesting because often you're trying to measure something like a transient because there's an impact that happens, a thump, or a change in state, or a system responds to that step change. So they're a little bit tricky to get because they're not steady state. They don't keep repeating. They only happen the once. And they've got surprisingly more energy in them over a wider frequency range than you first expect. So what we're going to do is a similar exercise as we've just done with those perfect sine waves, but we'll apply it to a transient. So first we're going to build our transient. So to construct our transient, we've taken a 50 Hertz sine wave, and then we've switched it on using a step function, and we've also made it decay using an exponential function. So in that figure you can see the combination of a 50 Hertz sine wave, a step function, and the exponential decay window, and that leads you with this sort of 50 Hertz decaying pulse. And what we're going to look at is what happens when we sample that. Now, here's our ideal signal. It's not really an analog signal, it's still a digital representation, but it's effectively sampled at like 100 kilohertz. So it's pretty much continuous. And that shows the rise time beautifully and the peak amplitude and all the rest of it's great. Now, remember that's the 50 Hertz sine wave, so we should be able to sample it to represent it quite easily. So here's what happens when we sample it at a kilohertz. We get a series of dots, and it's quite well represented in terms of the amplitude and also the rise time, and there's plenty of samples per cycle to work out what the detailed shape of the transient is. But a kilohertz seems like awfully fast to go if we're just talking about a 50 Hertz pulse. So let's drop our sample rate down to say 400 Hertz. Now 400 Hertz is still 8 times the bandwidth, right? But already you can see that we've truncated the peak, and we only have 1, 2, 3, maybe 5 samples in that first peak. Now, the way this is done, the way I've created these signals, we happen to have samples landing exactly on the zero crossings just because of the way I created those signals, but that wouldn't always be the case. So then let's go further. Let's go down to, say, 250 Hertz, which, like you said, if you were sampling a 50 Hertz sine wave, 250 Hertz would be heaps of bandwidth, right? But in this case, we've now got 3 samples in that first peak, and we don't get the correct peak amplitude at all. Now, obviously, from that, it seems that you have to sample. Why do you have to sample so much higher than you'd think when the content of the signal is only at 50 Hertz? So we've got our transient, and we've sampled it in the time domain, and we saw that we had to use a surprisingly high sample rate to accurately capture the transient shape, even though the underlying signal in that pulse is only 50 Hertz. There's a lot of energy in that switching on, and the exponential changes the bandwidth as well. So what people sometimes do is they'll grab a transient like that and want to look at the frequency content of it, and so they'll take a Fourier transform. Now, obviously, as we saw earlier with the ideal sine waves, when you take a Fourier transform of a steady state sine wave, you're going to get the right amplitude with no artifacts, as long as you've got a frequency bin that lands exactly on that frequency of the sine wave, because it is looking for sine waves that make that sine wave, right? It's almost a circular thing, right? When you take a Fourier transform of an arbitrary shape, obviously it's got a finite number of sine waves it can use to build that, and so you get leakage and stuff. So let's just have a quick look at how, if we take a Fourier transform of that transient, sampled at different rates, how that affects the spectrum that we get out. So here's the spectrum when we sample at 100 kilohertz. So this is like the idealized spectrum. It's almost continuous. Now we've always taken the same time period of data here, so the frequency resolution for all these is the same because the block of time is the same length of time. And then as we go to, say, sampling at a kilohertz, we pretty much match that original curve. That's looking like a really good estimate of that ideal transform. As we drop that sample rate, we start to get some deviations, and obviously the spectrum stops at the Nyquist frequency. So at 400 Hertz, we only get data up to 200 Hertz, and there's a bit of mismatch at that high and low frequency, as we're now talking about a bit of a different shape, really, when you remember what those time histories look like. And once again, if we get right down to 200 Hertz, where we only had 3 points representing that first pulse, so this pretty coarse triangle, that spectrum does look significantly different. Okay, so from that, we just see that we have to be careful with Fourier transforms to analyze the frequency content of these signals, because once again, if you haven't represented it nicely in the time domain, your frequency representation is going to be a bit off as well. And if you're after things like the peak amplitude and what the dominant frequency content is, Fourier transforms may not be the best way of doing it every time. You might be able to, maybe there are other methods of getting the same information. So one other approach would be to use time domain filters. So rather than grabbing your block of data and Fourier transforming it, you pass the same signal through a series of filters and look at the amplitude of the data that comes out. Which is a bit old school. You know, you can imagine the guys with the big light green boxes and the massive dials and the tape machine, and they'd record their signal and then they'd play it back and adjust the filter each time, and then they'd have an RMS meter and they'd see where the RMS meter got to and note that down and build up their spectrum that way. And when I first put together this simulation of that sort of thing, I surprised myself about what the output signals looked like, but then I had a bit of a think about it. So here's a picture of that original transient, and then also shows the output. I created a series of filters, effectively third octave filters, and passed the data through them, and each time we get a different waveform at the other end. And what I've done is I've just offset those time traces by a DC value, so you can see them separately in the time domain. And you'll see that in each of the different bands we get different levels coming out corresponding to what energy is in that band. But it's interesting to note that all of the signals that come out the other side do look like sine waves, and also have much lower amplitude than the peak itself. What's further interesting is that you would think the 50 Hertz band would pretty much pass the pulse straight through, because it's a 50 Hertz sine wave. We've just chopped it up a little bit. But if you look carefully, the 50 Hertz band is the red curve in this plot, and it doesn't, the pulse shape doesn't come back out the other end. A sine wave does. So when you think about this, any filter that's narrow enough, whatever you hit it with is going to generate signals in that narrow band, which by definition are just going to be sine waves, because that's what a narrow band of frequency is. So it's going to pretty much look like a sine wave. So if you are expecting out of your 50 Hertz band filter to get a representation of the 50 Hertz pulse, that's not going to happen, because all of those edges that make it into a pulse and the decay that makes it into that pulse, that's energy at other frequencies. So what I then did was I widened the filter until I started to see a pulse-like shape come through the other side. And to get a pulse-like shape to come out the other side, I ended up having a bandpass filter that was 10 Hertz to 450 Hertz, pretty much the whole bandwidth, to get something that looked a bit like the original pulse going in. Because obviously all those frequency elements have to be present to really accurately represent that pulse. And when you narrow it down, you just, by definition, get a sine wave out the other side. So even if you do that time domain filtering to pull out what the peak amplitude is, that's still not the same as the overall peak of that pulse. It's the peak in each frequency bin, which is a different thing altogether. Obviously, when we plot those peaks out, we get something that looks akin to the spectra. It has a rise at around 50 Hertz, because there is a lot of energy there, just not all of it. But it's much, much lower in amplitude than the actual peak in the time history of the full transient. So what other ways can we look at for estimating information about transients and how do they depend on sample rate. The AVA monitoring unit that we distribute and is used for ground vibration monitoring and construction monitoring, that uses a zero crossing kind of algorithm for determining what the frequency content of a transient event is, and it picks off the peak to tell you what the amplitude corresponding with that little snippet of transient is. So when you look at the zero crossings in that way, you can see from this figure that depending on the sample rate, your idea of where those zero crossings occur can be quite different. Now, admittedly, when I first did this at exactly 50 Hertz, because all of my signals are lined up and phase matched effectively, they all gave the same answer. They could all pick out the zero crossing because the zero actually happened at exactly the same place on all the signals. But I tweaked the frequency slightly for the purposes of this demonstration. So this transient pulse is at 48.83 Hertz, which just means that when you sample at different rates, the zeros don't quite land in exactly the same place, which is going to be true for the majority of signals you measure. So from this, you can see there's quite a dispersion in where those zero crossings occur, and the estimates of the frequency vary from, say, 28 Hertz through to, say, 32 Hertz. And the amplitudes also vary because each of those waveforms has been sampled differently, so from, say, 0.52 down to 0.47. Now, is that significant? Once again, it depends on your application, and that goes back to that first video we talked about where, what's this data going to be used for? That variation of, 5% might not be a big deal, but it might actually be a big deal. So it depends on your application. So obviously, the faster you sample, the more fidelity you've got about where those zero crossings actually happen. And when you take the differences between them, you're going to get a better estimate of what that frequency actually is. So with, hopefully that's a slightly different take on Nyquist theory than you've probably seen before, or just a bit more detail about it. I admit I've always taken Nyquist theories as obviously we're fine up to fs on 2 minus a bit, but it's surprising when you look in detail how far you want that sampling rate to be above your interested bandwidth if you want to represent things in the time domain. If you're doing steady state frequency analysis of things, it's completely different, and we'll do another video on how that works and why it's okay to push that boundary a bit. But if you're doing short transient type events with a lot of distributed energy, you do need to sample particularly high and analyze them in their own way. If they're fundamentally a time domain signal, and sometimes the frequency domain doesn't always make sense if you're describing them. So hopefully that's been informative, and I look forward to your questions on this. And like I said, in the next one we'll probably get on to talking about power spectrums and what kind of signals are best suited to that methodology, and how do you chop them up and how do you decide whether a signal is suitable or not.